Choosing the appropriate communication technology for remote monitoring and control involves assessing several options. For wired solutions, direct bury cable offers reliable communication by physically burying the cable in the ground. However, installation can be expensive and time-consuming, especially over long distances from 5,000 feet to 8,000 feet in length, as you are considering. Fiber optic cable presents another wired alternative, utilizing fiber optic strands for data transmission. While it provides higher bandwidth and data rates than direct bury cable, it also comes at a higher cost. Shifting to wireless options, cellular networks offer wide area coverage using cellular towers. This provides reliable communication, but performance can be affected by congestion and coverage limitations. LoRaWAN, a long-range wireless network protocol, is designed for low-power devices. It excels in providing long-range communication with low power consumption, but its bandwidth is limited. Microwave links provide point-to-point wireless communication using high-frequency microwave signals. These links offer high bandwidth and long-range capabilities, but their effectiveness can be affected by terrain and line-of-sight requirements. Programmable logic controllers, or PLCs, are commonly used for industrial automation and can communicate using various protocols. However, PLC generally require dedicated wiring for communication between them, which may not be feasible over extended distances. Satellite communication offers global coverage, but it can be an expensive option and may introduce latency issues. While traditional smoke signals are not suited for real-time data transmission, they can serve as a backup or emergency communication method. Based on the distances involved, the need for reliable communication, and the specific requirements of monitoring water tank levels, well pump operation, and solenoid control, LoRaWAN or microwave links are likely the most suitable options. To implement LoRaWAN, install LoRaWAN gateways at the clubhouse, water tank, and well locations. Equip each location with LoRaWAN-enabled devices designed for monitoring and control. Configure the devices and gateways to establish a mesh network for seamless communication. It's also critical to provide backup power to ensure continuous operation, even during power failures. When considering these options, there are a few factors to keep in mind. Firstly, cost is an important consideration. Direct bury cable and fiber optic cable have significant upfront costs for materials and installation. Cellular networks incur ongoing subscription fees. LoRaWAN requires investment in gateways and end devices, while microwave links involve costs for equipment and installation, as well as potential licensing fees. Secondly, bandwidth requirements must be considered. Monitoring water tank levels and well pump operation may not require high bandwidth, but the ability to operate solenoids and potentially transmit video data could necessitate a higher bandwidth solution. Thirdly, range and coverage are critical. The distances between the clubhouse, water tank, and well will dictate whether a particular technology can reliably cover the entire area. LoRaWAN is designed for long-range communication, while cellular networks rely on the availability of cell towers. Fourthly, power consumption is a factor, especially for remote locations. LoRaWAN is designed for low power operation, making it suitable for battery-powered devices. Cellular devices can consume more power, requiring a more robust power supply. Fifthly, reliability is critical for ensuring continuous monitoring and control. Wired solutions like direct bury cable and fiber optic cable are generally very reliable, but can be susceptible to damage from digging or other construction activities. Wireless solutions can be affected by interference or signal obstructions. Finally, security is important to prevent unauthorized access to the system. Implement appropriate security measures, such as encryption and authentication, to protect the data and control function. Before making a final decision, it's recommended to conduct a site survey to assess signal strength, potential interference, and other factors that could affect performance. Consider testing different technologies in a pilot project to evaluate their suitability for the specific application. Remember to consult with experienced professionals to ensure proper installation and configuration of the chosen technology. The National Electrical Code, or NEC, provides guidelines for safe and reliable electrical installations. When running power to the remote locations, ensure that all wiring and equipment comply with the NEC requirements. Consider Article 300.5, which addresses underground installations. This section provides requirements for the minimum burial depth of direct bury cables depending on the voltage and location. For example, direct bury cables operating at 600 volts or less typically require a minimum burial depth of 24 inches. Article 310.15 covers ampacity, the current carrying capacity of conductors. Select conductors with adequate ampacity for the load they will be carrying, taking into account factors such as ambient temperature and the number of conductors in a raceway. Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types. Article 250 addresses grounding and bonding requirements. Ensure that all metallic enclosures and equipment are properly grounded to minimize the risk of electric shock. Use grounding electrodes, such as ground rods or ground plates, to establish a connection to earth. Article 725 covers Class 2 and Class 3 remote control, signaling, and power-limited circuits. These circuits are often used for low-voltage control signals, such as those used for monitoring sensors or controlling solenoids. Ensure that the wiring and equipment used for these circuits comply with the requirements of Article 725. When running conductors underground, it's important to protect them from physical damage. Use conduit, such as rigid metal conduit or PVC conduit, to provide mechanical protection for the conductors. Consider using direct bury cable, which is specifically designed for underground installations. Direct bury cable has a tough outer jacket that provides protection from moisture, chemicals, and physical damage. When splicing conductors, use approved connectors and methods. Ensure that the splices are properly insulated and protected from moisture. Use heat shrink tubing or waterproof connectors to seal the splices. When installing equipment outdoors, use enclosures that are rated for outdoor use. These enclosures are designed to protect the equipment from rain, snow, and other environmental factors. Choose enclosures that are made of corrosion-resistant materials such as stainless steel or fiberglass. When installing grounding electrodes, ensure that they are properly installed and connected to the grounding system. Drive ground rods to a depth of at least 8 feet and space them at least 6 feet apart. Use approved connectors to connect the grounding conductors to the ground rods. Regularly inspect the electrical system to identify and correct any problems. Look for signs of damage, such as cracked insulation, loose connections, or corrosion. Test the grounding system to ensure that it is functioning properly. If you are not comfortable working with electricity, hire a qualified electrician to perform the work. Electricity can be dangerous, and it's important to take precautions to protect yourself from electric shock. Always disconnect the power before working on any electrical equipment. Wear appropriate personal protective equipment, such as gloves and safety glasses. By following these guidelines, you can ensure that the remote monitoring and control system is installed safely and reliably. Remember to consult the NEC and other applicable codes and standards to ensure compliance. Consider the specific requirements of the application, such as the distances involved, the bandwidth requirements, and the environmental conditions when selecting the appropriate communication technology. If the location of the proposed boys' camp is prone to lightning strikes, install lightning protection devices to protect the equipment from damage. Lightning arresters can be installed at the service entrance and at the remote locations to divert lightning strikes to ground. Use surge protective devices, or SPDs, to protect sensitive electronic equipment from voltage surges. SPD can be installed at the service entrance and at the remote locations to clamp voltage surges and prevent them from damaging the equipment. If the remote locations are subject to extreme temperatures, use equipment that is rated for those temperatures. Choose conductors with insulation that is rated for the maximum operating temperature. Use enclosures that are designed to protect the equipment from extreme temperatures. If the remote locations are subject to corrosive environments, use equipment that is made of corrosion-resistant materials. Choose conductors with insulation that is resistant to chemicals and moisture. Use enclosures that are made of stainless steel or fiberglass. If the remote locations are subject to vibration, use equipment that is designed to withstand vibration. Choose conductors with stranded conductors, which are more resistant to vibration than solid conductors. Use enclosures that are mounted on vibration isolators. If the remote locations are subject to rodent or insect infestation, use equipment that is designed to prevent infestation. Seal all openings in the enclosures to prevent rodents and insects from entering. Use rodent-resistant cable and wiring. By taking these additional precautions, you can ensure that the remote monitoring and control system is able to operate reliably in a variety of environments. Remember to consult with experienced professionals to ensure proper installation and configuration of the chosen technology and equipment. Before commencing the project, check with local authorities regarding permitting requirements for running electrical lines. Factors such as right-of-way access and environmental impact assessments could impact the project timeline. Coordinate with utility companies to ensure any underground or overhead utility lines are clearly marked before digging. This helps prevent accidental damage and service disruptions. The cost analysis should include not only the initial investment in equipment and installation, but also ongoing maintenance and operational costs. For example, cellular plans have monthly fees, while LoRaWAN gateways might require periodic maintenance. A detailed cost breakdown will assist in comparing the financial viability of each option over the system's lifespan. For the well pump monitoring, consider integrating sensors that provide real-time data on water flow, pressure, and pump motor current. This additional information can help detect potential problems early, such as pump cavitation or motor overheating. This allows for proactive maintenance, preventing costly downtime. When selecting solenoids for water routing at the tank, choose models that are rated for the specific water pressure and flow requirements. Also, consider solenoids with manual override features, allowing for operation even if the remote control system fails. This can be crucial for maintaining water supply during emergencies. Since the system will be used to monitor and control critical water resources, establish clear protocols for responding to alarms and system failures. Designate responsible personnel and provide them with adequate training on troubleshooting and repair procedures. Regular drills can help ensure a coordinated response in emergency situations. Consider implementing a data logging system to record sensor readings and system events over time. This historical data can be valuable for analyzing system performance, identifying trends, and optimizing operations. Data logs can also be helpful for troubleshooting problems and providing documentation for maintenance records. To enhance system security, implement multi-factor authentication for remote access. This requires users to provide multiple forms of identification, such as a password and a code sent to their mobile device, before gaining access to the system. This helps prevent unauthorized access even if a password is compromised. Regularly update the software and firmware on all devices in the system to patch security vulnerabilities and improve performance. This includes gateways, end devices, and any software used for remote monitoring and control. Establish a schedule for routine maintenance and inspections of the system. This should include checking wiring connections, testing sensors, and verifying the operation of solenoids. Regular maintenance helps prevent problems and ensures the system operates reliably. Given the distances involved, consider using repeaters to extend the range of wireless signals. Repeaters can be strategically placed to boost signal strength and ensure reliable communication between the clubhouse, water tank, and well. However, be aware that each repeater introduces a small delay in communication, so minimize the number of repeaters used.